So this is an example problem on how to use centripetal and tangential coordinate systems. This is a pretty classic physics problem. Usually you see this with something like a child on a swing or something like that. But the idea is you have a pendulum, some sort of pendulum system where you have a mass suspended from a massless, inextensible string of length L. And we're going to start this out at some height h above the ground, and of course this will swing down. And the question is going to be, what is the tension that we find in the rope here? Okay, so to do this, what I'm going to first need to find out is the tangential velocity of the, or I need to find the velocity of the ball here. All of the velocity is going to be tangential because we're assuming that L is not stretching or getting crumpled up. L remains extended, and so this thing swings down. All of the velocity will be tangent to the curve. Now, maybe I should say first, why do I need the tangential velocity? Because if I do a free body diagram of this system here, I'm going to have some mg and some tension that looks like this. And in this position, maybe we can see that all of the forces are in the centripetal direction. So if I'm going to solve for tension, I'm going to need to do something like this. Some of the forces in the centripetal direction is equal to ma centripetal. Let's pick towards the center of the circle as the negative direction. So that's going to give me a negative t and a positive mg. I'm going to write mg minus t is equal to m. And we also know our expression for centripetal velocity. It's negative v tangential squared over r. So I know the mass. I can determine this. I know the radius r is just going to be L. What I need is the tangential velocity. If I can do that, I can solve this problem. Let's go ahead and solve for the tension just because. But I can distribute the negative sign here and get this. So it looks like I'm going to get t is equal to mg plus m v tangential squared over L. I'm going to replace the r with L. And just for my own personal benefit, I'm going to factor out the m because I like it to be as clean as possible. V tangential squared over L. So if I can figure out what V tangential is, I can determine this pretty easily. Well, what's V tangential? We've already solved problems similar to this in another portion of the class. If you remember that, or if you're in my class, we did. Conservation of energy is probably going to be the easiest way to go about this. If I look at the system between here and here, and I recognize that it's starting from rest, I can write down the conservation of energy equation like this: K initial plus U initial plus work due to non-conservative forces plus equals, and that looks like a not equals. It's associating equals. K final plus U final. There's no friction or air resistance. There's not going to be any work due to non-conservative forces. If I set my 0 point here, put my origin at the bottom of the motion, there's no potential energy. This is all stuff we've talked about before. So if this is the first one of these problems you've seen, go back and find the conservation of energy example problems. If I drop it from rest, there's no initial kinetic energy. So what I get is initial potential, which is all gravitational, mgh, height above the 0 point is h, is equal to 1/2 mv final squared. My m's are going to go away, and I'm going to get hopefully a familiar result by this point, root 2gh. This is the same result we get if we use kinematics or conservation of energy. Of course, it has to be. This is a very, very, very common result. This is one of the reasons I believe in symbolic solutions, because you see this so many times you can go, oh, I know I'm right because I've seen this about 1 billion times. Okay, so I'm going to plug in for V tangential, root 2gh. It is squared, so let me go ahead and square it. Therefore, tension is equal to m times g plus this quantity squared gets me 2gh over L. And that is my answer. I can, of course, clean it up a little bit if I want to, and I always want to. 1 plus 2h over L. And check dimensions. 1 is dimensionless, H and L will both have dimensions of meters, so that cancels. This is good. I like it like this because this tells you something about the physics, right? If this was not moving, if it had no tangential velocity, if it was just sitting here still, what would the tension be? It would just be equal to mg, right? We've done that. That was where we started doing Newton's second law problems. Have something sitting here with a tension and gravity. The tension is just mg. But now it's something bigger than mg. It has to be bigger. 1 is positive. H and L are both positive. This number is going to be bigger than 1. So the tension increases because we know that the tension is a function of that tangential velocity. So if it has a velocity, it's going to have a greater tension than if it's sitting still. But I like it like this because this tells us if it's not moving, we expect that. But if it is moving, we expect something more than that. And this lines up very nicely with that.